So in the last video, we took a look at an extensive proof of a special case for L'Hopital's rule, but now we want to start trying to figure out how exactly we can use it. And so here in example 1, we're going to take a look at those two limits that we used back in the opening example. And we're going to go through or the opening motivation, excuse me, and we're going to see how each of these limits could be calculated. So let's go ahead and take a look here at part A. Here I have a limit of the natural log function of x over x minus 1. We've already recognized here that this function kind of exists in the form of 0 over 0. And this becomes an important thing to note because if I want to use L'Hopital's rule, I need to note first that I have two differentiable functions and that I'm going to be working with an indeterminate form of 0 over 0 or an infinity over infinity. Pluses and minuses don't matter. So I can see here that yes, my natural log function is continuous near 1. My polynomial function is definitely continuous near 1. Or sorry, differentiable near 1. And I have the form of 0 over 0. So now I know that I can use L'Hopital's rule. So let's think about what L'Hopital's rule would actually state here. Remember that L'Hopital's rule states that the limit that we want to calculate is equal to another limit where x is still approaching the same value, but we would just end up having to take the derivative of the numerator and the derivative of the denominator separately and place them back in the numerator and denominator of our new fraction. So the derivative of our natural log of x function would just be 1 over x. And the derivative of our polynomial function would be 1 minus 0, or just 1. Now, it's right here where I'm going to go ahead and I'm going to add a little bit of notation. Right above this equal sign, I always like to put a little h to indicate that I went from this first step to the second step by applying L'Hopital's rule. And this is very standard, common notation in mathematics. If you were to say, like, go look at solutions to, like a textbook or something like that that teaches this, they're often going to put that h there. And it's to help try to distinguish when I'm just doing, say, like an algebra move from when I'm actually doing this specific calculus move. Okay, so all I know right now is that the answer to the limit that we want has the same answer as this limit over here. So if I can figure out what this limit is, I'm good to go. So let's just pretend now that this is the only question that we've ever been concerned with. Well, I should note first off that this is really just going to be a limit of 1 over x, right? Because 1 over x divided by 1 is just 1 over x. Notice I don't have any need to put an h here because I'm just doing some basic algebra, right? I'm just dividing by 1. Oh, and now I realize I have a nice continuous function at x equals 1 here. And so I can just do a direct substitution. I get 1 over 1, which is 1. So this limit has answer 1, and so our starting limit has answer 1. Notice this is why this is kind of really strange. In this instance, 0 over 0 in our limit form ended up producing a value of 1. Okay, well let's take a look here at part B. In part B, we already saw in the opening motivation that we kind of were going to have the form here of infinity over infinity. Now again, since I have a differentiable function up top and on bottom when x is moving towards infinity, and I have the form infinity over infinity, I can again think about using L'Hopital's rule. So I set up my original limit, and I say that this is going to be, by L'Hopital's rule, equivalent to a new limit where I just replace again the top and the bottom with their derivatives. So notice that the steps here look almost identical. Again, I can still do a basic algebra move of just rewriting this as 1 over x, but now I can see that if I'm working with 1 over x as x goes towards infinity, that means that my denominator is going to continually get larger and larger and larger, and of course then this value should be 0. So this is how I would actually implement L'Hopital's rule in specific questions. But notice again that there are two things that I have to check every time. I need to make sure that my functions are differentiable functions near the value that I'm working with, that is, near the value that x is approaching, and that I have to make sure that I have one of the two indeterminate forms, a 0 over a 0 or an infinity over an infinity.